Hi guys, I wanted to finish the lesson today. We have to go over 6 and 7. 6, stretching and compressing materials. So we talked about the spring constant K being an indication of how stiff a spring is. Well, when you're dealing with a solid bar, the bar is actually kind of rigid, but it still stretches out a little bit. So it actually still has a spring constant, but it's more common when you're dealing with like a metal bar to use a proportionality called Young's modulus. And what we're going to do is see the hidden relationship between the spring constant and Young's modulus. So first, let's review Hooke's law. If you graph the data from Hooke's law, on this x-axis, we have the change in length. That's usually referred to as the elongation. And on the y-axis, we have the force. Well, if you use a bigger and bigger force, the elongation, the amount it stretches out, is going to be bigger and bigger. And this is true whether you're using a spring or whether you're pulling and stretching a steel rod. And when you plot this data, it's a direct relationship, and the slope is equal to the spring constant. And the spring constant has units of newtons per meter. Okay, so moving on to the next page. So here we have a bar, and the bar is, let me get my pen working, attached to the wall over here. Now, somebody's going to come along and grab this bar with their hands and their thumb over here, and they're going to pull the bar out this way. Maybe it's a machine or something, yes? And when they pull it this way, it stretches out a distance delta L. But of course, the bar doesn't want to stay out there like that. The bar wants to pull itself back in. So this pull back in, due to the bar's elasticity, that's known as the restoring force. So the restoring force, it wants to pull the bar back into its regular size. Now recall, Hooke's law said that the amount of force is directly proportional to x. And remember, x is the change in the length. Well, this is called the spring constant, and it indicates the stiffness of the spring, or in this case, of the bar. Now, this spring constant, it turns out, depends on three things. It depends on, if you're dealing with a bar like this, it depends on the cross-sectional area. This area right here. It depends on the length of the bar. That would be like the original length. And then it depends on this constant y, which is called Young's modulus. And what Young's modulus really represents is the type of material. So you start off with Hooke's law, And we're going to substitute in that expression for the K value. So it becomes force is equal to, instead of writing this K, we're going to substitute in this expression, the three things that K is equal to: Young's modulus times the cross-sectional area of the bar over the length of the bar times X. And then we're just going to algebraically rearrange this. I'm going to divide both sides by A, so I get force divided by A equals, and then I'm going to move this L underneath the X, so it's going to equal Young's modulus times X over L. But remember, X is the elongation, which is delta L. So the force over the area is equal to Young's modulus times delta L over L. So the force is how much force is pulling the bar out, or how much the restoring force is, divided by the cross-sectional area of the bar. Y is kind of like the new spring constant. It depends on what material it is. Delta L is the elongation, the change in length. And L is the original length. And it turns out that these terms have their own names. The force divided by the cross-sectional area right here, that's known as the stress. And then, of course, this Y right here is Young's modulus. It's like a new proportionality constant indicating the stiffness. It's related to the spring constant, but not the same. And this change in length over the original length, that's known as the strain. So force divided by area, stress, change in length over the original length is strain. So we start off with Hooke's law that had the spring constant, and we ended up with a new relationship: stress equals Young modulus times strain. So the units for stress which is this part right here, are going to be like what you see is what you get. Newtons divided by meters squared. Newtons for force, meters squared for area. And if it's due to the bar being stretched out, it's usually referred to as the tensile stress. Interesting, the units for strain, the strain is the change in length over the original length. Well, the change in length are meters, and the original length is in meters, so they end up canceling out. So the strain has no units. So here are the values for Young's modulus. You remember that's the Y value for various different materials. But there are also Young's modulus values for biological materials like tooth enamel, compact bone, spongy bone, your tendon, cartilage, a blood vessel. So these right here, these values are the Y values in the formula. Stress equals Y times strain. And remember what stress is? It's the force exerted on the object divided by the cross-sectional area. And the strain is the change in length divided by the original length. These values go in for the y. So that takes care of, where's my pen? Stretching and compressing. And last, we're just going to look at a quick example of the forces and torques on the body. So here we have an ankle, and what we're going to end up doing is figuring out how much force this tendon puts on the heel. This tendon is going to be lifting up the heel when somebody stands on their tippy toes, and that's our first mission. Now, your ankle pivot around this point here. It's called the ankle pivot. Now, if the person is a 61 kilogram woman, the first thing we're going to have to do is figure out how much she weighs, because that's her mass. So using the formula Fg equals m times g, if she was picked up and dropped and put in free fall, she would have a downward acceleration of 9.81 meters per second squared. And the only force acting on her, if we imagine her in free fall, would be the force due to gravity. So if I multiply this out, what do I get? 61 times 9.81 equals roughly 600 newtons. So if this is the floor right here, if the woman has a weight of 600 newtons, the floor is going to have to support all of her weight. So the force due to the floor is going to be 600 newtons. And our question is, how much is this tendon over here pulling upward on the heel? So the next thing we have to do is a torque problem. So this is going to be the pivot point right here. And if the person's standing still, they're in static equilibrium. So we know the sum of the torques, also known as the net torque, has to equal 0. Well, this force right here is going to be putting a torque about that point. And it's the left side, so it would be making that sucker go counterclockwise. I'm sorry, clockwise. And that would be negative. So it's going to be negative 600 newtons times the perpendicular distance between the force and that pivot point is shown right down here, 15 centimeters, 0.15 meters. Now, the tibia bone is pushing right down on that ankle pivot, but the force is right through it, so that particular force doesn't exert a torque because it's right through the pivot point. This tendon, though, is pulling up on the heel, and this perpendicular distance, we're going to have to subtract 20 centimeters and 15 centimeters, so that's going to be 5 centimeters. So the tendon force times 0.05 meters equals 0. And this is positive because that tendon is going to make the body try to go counterclockwise around that pivot point. And if you solve this for T, you get 1,800 newtons. That's right. The person only weighs 600 newtons, but that tendon back here is going to be lifting up and pulling up on the heel with a force of 1,800 newtons. And last but not least, I was going to give this to you guys as a VVOX problem. If the floor is pushing up on the tippy toes with a force of 600 newtons, the tendon is lifting up on that heel with 1,800 newtons. I should draw that much longer. It's a bigger force. Just look at the up and down forces. If this thing's in static equilibrium, the up forces have to be balanced out by the down forces. We're trying to figure out what this force is right here. The force of the tibia bone on that ankle. So the easiest thing to do is just to say, hey, it's in static equilibrium. The sum of the forces in the y direction is equal to 0. So you have plus 600 newtons plus the force to the tibia going down, so that's going to be negative, plus the force due to the tendon, 1,800 newtons going up, so that's positive, and then it's going to be equal to 0. And if I add this over side, I get force due to the tibia, and 600 plus 1,800 is 2,400. So that's right, ladies and gentlemen. When you stand on your tippy toes, your tibia pushes down on that ankle with a force of 2,400 newtons. And remember, this is a woman who only weighs 600 newtons. So it's kind of fascinating the way those forces get magnified. All right, that's the end of the lesson.